Hello, my name is Mark Peterson from Theia Technologies. I am the Vice President of Advanced Technologies. I'm going to talk today about using Theia's patented linear optical technology for correcting barrel distortion in wide-angle lenses. This is an all-optical distortion correction technology. No software is required for de-warping the image. Distortion correction is done in the lens optically and can be used for lenses up to 135-degree field of view. Theia Technologies was founded by myself and Jeff Goman in 2006 to take advantage of what would become our patented linear optical technology. We do design and worldwide sales from Oregon in the US, and we have a Japanese lens manufacturing partner that produces high-resolution lenses to our specifications. Both our manufacturing partner and Theia Technologies are ISO 9001 certified, and our partner has other certifications for manufacturing and automotive. Our primary markets are security and machine vision, including robotics applications. And we have 3 families of lenses that use our patented technology, which I'll talk about, as well as other high-resolution standard and telephoto lenses. Theia has made some custom lenses for many customers, including NASA, for the Global Hawk weather survey drone, seen here flying at 20,000 meters over the Sierra Nevada mountains. NASA is using one of our ultra-wide angle lenses, the SY-125. This includes our linear optical technology, and they like it because it shows the curvature of the Earth. Theia was the main lens provider for the Hero 2 and Hero 3 and 3 Plus cameras from GoPro. This was a very high volume custom lens design program. Although this is a wide angle lens, we did not use our distortion correction technology in this lens because the customer preferred the barrel distortion look. ARRI is a German cinema lens company that uses our patented linear optical technology in their UWZ lens. This is a lens for the Red and Blackmagic cinema cameras and has been used in a few recent blockbuster movies. And the Japanese space agency JAXA. The Hayabusa 2 project landed on the asteroid Ryugu in September of 2018 and returned with a sample from the surface of the asteroid earlier this year. Theia's linear optical technology was optimized and miniaturized for the 2 cameras on the Minerva remote vehicles. These were used to collect samples from the asteroid surface and also take close-up pictures. So what is barrel distortion? As an object point moves farther from the optical axis of the image point gets compressed. This purple undistorted point in the left gets compressed in the distorted view as a function of the distance from the center. It's expected to be imaged where the white dot is, but due to the distortion of the lens, it's moved in slightly to where the purple dot is on the right. So you can see that a line of points in the image that makes up a straight line in the object. Each of these points is at a different distance from the optical image center. And because of the difference in distortion based on the distance from the center, the points get compressed and show up as a curve in the image. For some applications like the full sky Meteor survey, which uses a fisheye lens, this curvature is not an issue. It's more important to capture the entire hemisphere than to keep the lines of the building straight. However, for other applications such as mapping and navigation, the image on the right shows that an image that has been distortion corrected would really be a benefit in this application. Many of the principles of distortion correction apply both to the rectilinear lenses, including Theia's linear optical technology, as well as image correction using software, with 2 exceptions. Firstly, a lens with barrel distortion reduces the image resolution at the edges of the image. If the original doesn't capture high enough resolution, as seen in the picture on the left, it's lost and software correction will not be able to replace it. With the rectilinear lens, the resolution at the edge of the image is seen on the right, it will be higher. And secondly, software correction takes processor time and power, whereas optical distortion correction is immediate. There's no latency, which is very helpful for navigation applications, such as controlling robot arms or self-driving cars. Here's an example. On the left, you see a lens with barrel distortion. The person at the edge is 50 pixels wide in this image. In the same positions, using Theia's rectilinear lens, that person is 70 pixels wide, which is a significant difference in the resolution at the edges. However, this increase in resolution at the edge means resolution must decrease elsewhere. In the center of an image, a person will cover fewer pixels in the rectilinear image and will appear farther away from the camera. This is not so good if you're GoPro and you want the person in the center to be the hero, but for machine vision applications, the less distortion, the better. This curvature is not always desirable. However, it's present to some degree in most wide-angle lenses, with the exception of these specialized rectilinear lenses. These rectilinear lenses are designed with constraints that limit the barrel distortion created in the image. As a result, they're generally more complicated, requiring more internal lens elements, and are generally a bit more expensive. For rectilinear lenses, finding the position of an object point on the sensor can be simple. Knowing the position is important if you're looking for controlling a robot arm, or you want to automatically measure the area of an image using an edge finding algorithm. In either of these examples, having the barrel distortion, which affects the position of an image point as you get further away from the optical axis, this can make this challenging. But at the praxial limit and for long focal length lenses and slow f numbers, you can draw a simple triangle to figure out the position of a ray in the image. As the field of view increases, the designer must put more and more weight on the rectilinear constraints at the expense of other constraints, such as image focus or cost. Field of view of 60 degrees or less can be fairly easy to correct optically, and there are even lenses up to 100 degrees field of view or more. The Canon EF 11-24 has 115 degree horizontal field of view at f4, and the Kowa LM4HC lens has 112 degrees at f2.4. However, at some point, it becomes too difficult to maintain the rectilinearity. Wider fields of view cause extreme difficulty for rectilinear lenses and usually require a large A-sphere for the first element. There are a couple of big disadvantages of this. Firstly, the first lens element is usually the biggest in the system and is generally one of the most expensive elements because of its size. Secondly, the lens element must be very aspheric, which means making a molded precision glass element is difficult because molded glass elements must be kept close to their spherical shape and to maintain the high resolution. Canon achieves this ultra-wide field of view using 4 A-spheres, which are mildly aspheric in their 11-24. But Kowa uses an expensive large front A-sphere as the first element. The first element could be made of plastic, which would be less expensive and can also be very high resolution, but it has difficulty with AR coatings cracking due to the thermal expansion and has poor scratch resistance for cleaning and general use in rough environments. Even if you can accept the cost and environmental issues of a plastic element, it's still difficult to widen the rectilinear field of view even further. Theia, however, has developed an optical design to correct distortion and maintain a rectilinear image up to 135 degrees field of view. This is the widest angle rectilinear lens available, with an equivalent focal length of about 8 millimeters at the full sensor size. Actual focal length is 1.3 millimeters because this lens is designed for a smaller 1/2.5 inch sensor, which is much smaller than the DSLR sensor size. But the linear optical technology used in this lens has also been used for the larger DSLR sizes, such as the one sold by ARRI. We use 3 A-spheres in our ultra-wide lenses, but due to our unique design, it allows us to keep the lens diameter small without the need for the large front aspheric element. As a result, the cost is kept low compared to other ultra-wide lenses. One noticeable effect of ultra-wide-angle lenses and software correction of ultra-wide-angle views is what we call 3D stretching. If the object in the photograph has any depth along the optical axis, such as the tables at the edge of this image, they will appear to be stretched in that direction. However, if you want to image something flat, such as a wall or an LCD screen, unlike the tables in the previous image, all the bricks appear the same size in this image as they should, because the object has no depth along the optical axis. In this instance, the rectilinear lens makes the image look good because the object is basically flat. Here's another example. You can see the two cars are in the same plane away from the lens, and so they have the same width. However, because car B is closer to the edge of the image, and each of the cars has depth along the optical axis, they will appear to be stretched. And stretching increases as you get further away from the center. The stretching is related to the tangent of the angle of the view of the object. You can think of it like projecting rays from the camera to the different points of the object and onto a plane. At the edge of the image, there's a lot more side of the car visible, and so it will appear to cover much more of the image plane and will look stretched. Theia has three families of lenses using linear optical technology distortion correction in the lens. These lenses have resolutions of 3 megapixels, 5 megapixels, and up to 4K. The widest angle lens is the SY125 with field of view of 135 degrees. This has about 7% distortion in the corners, making it almost rectilinear, whereas typical lenses with this wide field of view will have 60 to 70% distortion. The SY110 and the SL183 both have almost 0% distortion, which makes them very close to the true rectilinear lenses. All these lenses are available in C and CS mount. For applications where you need a ultra-wide field of view, but don't want to do the software correction to get a rectilinear image, any of these lenses would be a good choice. We also have many other options for lenses, ranging from motorized lenses to mid-range lenses to telephoto, all very high resolution. The ML610, for instance, is our 2/3 inch lens, 6 to 10 millimeter focal length. And although it is a wide angle lens at 6 millimeter side, it does not use our linear optical technology. It is high resolution, up to 300 line pairs per millimeter. Our lenses have been used in projects from the depths of the ocean to Arctic ice monitoring to outer space. One more example is the Toshiba space chair. In this TV commercial for Toshiba, they attached our lens and camera to a weather balloon along with chair and flew it up to 33,000 meters so they could see the curvature of the Earth. Their tagline was "Armchair Viewing Redefined." After the balloon popped and everything fell back to Earth, they were able to safely recover the video. So at Theia Technologies, we'd like to help you take your project to new heights with ultra-wide redefined. Again, my name is Mark Peterson, and I thank you for your time. You can visit our website at www.theiatech.com, and from there you can request a sample to evaluate linear optical technology for yourself.